Tonight's video we're going to talk about acid-base titrations, and what an acid-base titration is, as you saw in the previous video, is going to be when a known concentration of an acid or a base, we'll say a known concentration of base is slowly added to an unknown concentration of an acid, and that can be vice versa. We can have a known concentration of acid added to an unknown base. We use that one to figure out the other. What we're going to do is we're going to use that equipment that was in the previous video and an indicator which is going to change color at what's called the equivalence point. An equivalence point is going to be when you have equal number of moles of hydrogen ions coming from your acid and hydroxides coming from your base. And so what this can do is we can monitor the pH as the base is slowly added, and we can set up what is called the titration curve, which looks different depending on whether it's a strong acid being added to a strong base, or a weak acid to a strong base, or a weak base being added to a strong acid. So this one here, this titration curve here is going to be 50 mils of a 0.1 molar HCl. So this is going to be a strong acid, and it's having 0.1 molar sodium hydroxide, a strong base, added slowly to it. So what's going to happen is if you take the negative log of 0.1, you're going to get a pH of 1, which is where our graph starts right here. And as we slowly start adding sodium hydroxide to this, you see that the pH doesn't necessarily rise very quickly. It's just rising slowly. What's happening in this reaction is the hydrogen ions are reacting with the hydroxide ions just to form water. Now that's the net ionic equation. The complete equation is HCl is reacting with sodium hydroxide to produce sodium chloride plus water. But the sodium chloride, the sodium and the chlorine are spectator ions, so that would give us a net ionic equation of just the hydrogen ion plus the hydroxide ion. And so as we get up to like 45 milliliters of the sodium hydroxide, it's being all consumed by the hydrogen ion, and there's still excess hydrogen ions left. When we get to our equivalence point, you get this rapid rise up, and there's our equivalence point there. pH is 7, and we could use a couple different color indicators. You could use phenolphthalein or some methyl red. These both indicate within this range. We'll be talking more about how to choose an indicator for a titration later on. Okay, let's do a calculation involving this type of idea. So here's our calculation. We're going to calculate the pH when 49 milliliters of sodium hydroxide that's 0.1 molar has been added to 50 milliliters of a 0.1 molar HCl. So it's a strong acid-base reaction. So we're going to write our balanced equation once again. Sodium hydroxide being added to hydrochloric acid, yielding sodium. I said sodium chloride over there. I should have said sodium hydroxide on our reactant side. And we're also making water. And if we net ionic, this is going to be the hydrogen ion plus the hydroxide ion. And I understand I did write that hydrogen ion under the sodium hydroxide. I know that's not where it came from. H2O, just like that. So we're going to write a balanced equation. It's balanced. Number 2, let's calculate the number of moles of our hydrogen ion, or our HCl. And so we're going to do this using the molarity formula. Molarity equals moles per liter. And so it told us up above that we have a 0.1 molar HCl solution. And we had 50 milliliters, and I'm going to convert the 50 milliliters to liters by dividing by 1,000. And so it lets me know that I have 5 times 10 to the negative 3rd moles of my hydrogen ion. We're going to do the same exact thing. Calculate the number of moles of the hydroxide of the sodium hydroxide using the molarity equation again. Molarity equals moles per liter. It told us we had a 0.1 molar solution, and we have 0.049 liters. And so when we solve it for moles, we get 4.9 times 10 to the negative 3rd moles of hydroxide ion produced. Now, the next thing that we want to do is we want to, okay, so what we're going to do next here is we are going to do kind of a modified ice table. It's not really an ice table. We're going to take our hydrogen ions, we're going to take our hydroxide ions, and we're not going to worry about the water because that doesn't affect pH. And we're going to do a before, and we're going to do an after ice table. So before this reaction, we have 5.0 times 10 to the negative third moles of hydrogen ion. We have 4.9 times 10 to the negative third moles of the hydroxide ion, and who cares about the water for this point? Now, what we're going to do is just subtract the smaller of the two values, and so the smaller of the two values is going to be 4.9, so we're going to subtract that from both sides. 4.9 times 10 to the negative third, 4.9 times 10 to the negative third, and so there's not going to be any hydroxides left over at the end. They're all consumed, but we'll have a little bit of excess of those hydrogen ions. It's 1.0 times 10 to the negative fourth moles. And so that's an important idea because we want to calculate the pH. So before we can calculate the pH, what we're going to do is we need to recalculate molarity. And so remember again, molarity is equal to the number of moles per liter. And so as we just determined, we have 1.0 times 10 to the negative fourth moles of the hydrogen ion. And now for our volume, we're going to add together to the two values. Now we had 50 mils of the hydrochloric acid, we had 49 mils of the sodium hydroxide, so that's going to give us 99 milliliters. And so we're going to do 99 milliliters divided by 1,000 to turn it into liters, or 0.099. Run this through my calculator, and I'm going to get an answer of 1.01 times 10 to the negative third molar for my hydrogen ion concentration, and I'm almost there. Last thing I want to do is calculate the pH. So to calculate the pH, obviously, we just take the negative log of the hydrogen ion concentration, 1.01 times 10 to the negative third, and we get a pH of 3. So it shows us that after adding 49 milliliters of sodium hydroxide to 50 milliliters, there's still a whole bunch of hydrogen ions left over, and that causes that solution to still be acidic. And if we scroll back up to our graph, we can see this on our graph. And so that 49 milliliters on our graph is going to be, somewhere right in this vicinity right here. And yeah, well, that was not a very straight line, but there's our, well, I can't draw a straight line to save my life right now. But there's our pH, it's 3. So really that one drop more or 2 drops more that just pushes us over the edge, the equivalence point, causes that pH to shoot up from 3 right to 7. And then maybe a couple more drops would cause that pH to shoot up even further over that. And so that's why titrations, that whatever's being added into your Erlenmeyer flask, you have to do it very slowly. Now I'm going to leave you with one additional problem, and I'm not going to give you the answer. I want you to see if you can do the answer, and we'll talk about it tomorrow. So if we had the same reaction going on, how about you calculate the pH after 51 milliliters of sodium hydroxide, which was 0.10 molar, is added to the original 50 milliliters of HCl. So this is a brand new equation. Now we're obviously going to have an excess of sodium hydroxide. So see if you can calculate that pH, and I'll give you a hint. It should be basic. Have a nice evening.